There's nothing radiation protection focused. There's anything radiation protection focused which you need assistance with, you're unsure of, you feel like you need some intervention, please get in touch with me. I will be speaking to various people within RU almost on a daily basis, so particularly the industrial hygiene team. So you can almost see me as being an advisor who is not part of the organization. Okay, so I'm not part of RU, but I can advise you on RU, and it's important that I'm not part of RU because it means I'm not influenced by any politics happening within Rumela. It's independent advice, and it will always be independent advice. Okay, so I'd encourage you to get in touch with me as much as you can. Those of you who are in the field, I'll give you my cell number so you can get me on WhatsApp. You know, if you just have a quick question, sometimes it's easier to use WhatsApp than to, you know, write an email. So I'll provide that to you as well. What I wanted to run through today, well, I wasn't sure what sort of level to pitch it at because I didn't know what experience you guys had. I'll bring this material up. So I've put something together for this. I'm just going to spotlight myself so you can see me nice and clearly. Just bear with me. Got a couple of screens here that I need to work out what's going where. Okay, so a lot of what I'm going to talk about right now is very much going to be things that you know very well. Okay, I will skip through a lot of these slides because based on your educational background and your experience, I think you all know most of this, but just a very quick refresher, and this might be useful as well because this will mimic a lot of the material that's delivered to RU personnel. So for awareness training for, you know, people working at RU. In terms of explaining radioactivity, the way we tend to explain it, obviously we don't go down to the fine detail of nuclear physics because for many people that is not going to make any sense. So we need to keep it very, very simple when we're doing any awareness training. And again, those of you who are going to be based in the field will almost certainly at some stage have to deliver awareness training. It might be something that's done quite frequently. So the level we kind of pitch it at is we talk about the atomic structure just based on, you know, your three atomic components, so electrons, protons, and neutrons, and it's just to give a very high level overview of the model of the atomic structure that we use, the basic model. Okay, we're only looking at the very basics here, explaining that, you know, the number of protons will determine which element we have, the number of neutrons determines which isotope we have, and the number of electrons determines the overall charge. So we just keep it really, really simple. And the reason that we introduce this is to basically explain the terminology used for describing different radioactive isotopes, or just different isotopes. So giving a description of the fact that we use something called the atomic mass to describe which isotope we have. Okay, so the example I always use is carbon-12 because it's an easy one. The numbers are easy. We've got 6 of everything. So 6 protons makes it carbon. 6 electrons in this example means it's a neutral atom. There's no overall charge. And 6 neutrons makes it the most abundant form of carbon, carbon-12. At that point, we can introduce a second isotope, and this is where we introduce the notion of radioactivity. So carbon-12 is an example of a stable isotope. Carbon-14 is, of course, an example of an unstable isotope. The only difference from our basic model of the atom is that the carbon-14 atom has 2 additional neutrons in there. So radioactivity is in general a consequence of the forces at play within the nucleus. And those forces are between protons and neutrons, neutrons and neutrons. So there are lots of forces interacting, very complex system. And in some cases, there is additional energy stored within that nucleus that wants to be released in some manner. And it does that through releasing ionizing radiation. Okay, now ionizing radiation, we don't get down to the fine detail of exactly how the interactions take place and why it's ionizing. We just talk about the fact that it is ionizing and it's distinct from non-ionizing radiation. Okay, so if you're delivering awareness training in the field, and someone says, what about Wi-Fi? What about radio waves? Why doesn't that do the same thing to us? Are they damaging to us? Well, how would you answer that in a simple way?
Yes.
So the simple way to put that one away is simply that they are
not ionization.
Yeah, exactly. It's not ionizing radiation. Those other types.
Not ionizing radiation.
And the key difference between ionizing radiation and non-ionizing radiation is ionizing radiation interacts with the atoms at an atomic level, rather than at a macro level. So non-ionizing radiation can cause damage, but it does it through transfer of energy in the form of heat. So it vibrates things and it makes things move, and it like a microwave oven. Whereas ionizing radiation can actually interact with the atomic structure itself. Yes. And this is the reason it's so different, and we have to make a distinction between the two. So ionizing radiation has the ability to strip electrons away from other atoms. It has the ability to break chemical bonds, and that means that the damage caused by ionizing radiation is much higher for the energy involved. Yes. Okay, the amount of energy you'd need to break chemical bonds through thermal interactions is huge, whereas the energy involved in an ionization event is really quite small. So small amounts of energy for large amounts of damage. Process of ionization is essentially radiation interacts with the atom, gives energy to the electrons so they can escape from their orbit. Now, when you have chemical bonds involved, that can mean that those bonds are broken. If you've got very complex structures like biological cells, then that can lead to permanent damage to that cell, can alter the way that it operates, and in some cases can actually kill the cell. Now, the three types of radiation that we are concerned with at RU are your primary radiations. Now, when we're talking about norm, we only go as far as talking about these three. So alpha, beta, and gamma.
Okay.
There are neutron sources in the field as well. Okay, but the focus really of this contract is primarily on the norm. We'll see if that changes over the next few years. It may be that the RU want to get you involved in auditing contractors that use sources as well. At the moment, that's not the plan, but there are neutron sources used through the field as well for well logging operations. So alpha, beta, and gamma are our primary radiations. As you know, alpha is the most heavily charged. It's the heaviest of these three. It causes the most damage, but it's the easiest to stop. Alpha radiation, essentially a helium nucleus. Where we find alpha radiation, I don't know what the situation is in Iraq, but certainly in the UK, and this isn't the same across Europe, but in the UK, most of our domestic smoke detectors, so the ones I have here in my house, contain a small alpha source. Do you know if that's the case in Iraq? Do you use ionizing smoke detectors?
Smoke detectors.
Yeah, so like your fire detection in your own home. Yeah. Does it use
most use alpha
Most of them use an alpha source, yeah. So there's some countries where it's not common at all, and they use optical detectors, but they're not as good. So these ionizing ones, source of alpha radiation, there aren't any other intentional sources of alpha radiation used at RU. And as far as I'm aware, the smoke detection throughout the sort of office buildings is largely optical. So I don't think ionizing smoke detectors are really used at RU. I know there is one in the industrial hygiene office. That I can't remember who got it, but someone went and bought it from Basra Market, and it was used for a time as a test source for the contamination meters, because you do get quite a good reading with the scintillation probe on it.
Yes.
Okay, so outside of that, alpha radiation, we find alpha radiation being emitted by norm. Now, it doesn't matter where the norm comes from. It doesn't matter which system it's from. Alpha radiation is always emitted. Okay, it's the one that is always present, and it's one of the reasons that norm presents a reasonably significant internal pathway risk. So that's from inhalation and ingestion of material.
Also through wind.
Yeah, I mean, if it spreads and people can breathe it in, it does pose a significant risk. So containment is one of the most important parts of norm control. Sealing open ends of equipment, making sure that waste is properly contained and stored in a manner that prevents dispersion. Alpha is very easy to stop. For most alpha radiation, the dead layer of skin on the outside of your bodies will actually stop it. It's not the case for all alpha radiation, but for the majority of it, some alpha radiation can lead to a skin dose. But generally, at the levels we're talking about, not really a risk. So it's an internal pathway that we're concerned with. Beta radiation's quite similar. Okay, beta radiation can penetrate through more material, and it can give us a skin dose. But the levels that we are generally dealing with for norm, the beta radiation that's emitted is primarily associated with an internal dose risk.
Yes.
Now, there are not that many uses of beta radiation. Okay, so other than finding it in norm, there's not many other situations where we would find beta radiation. There is one exception at RU, and that's at the Rumaila power plant. So I don't know if you're familiar with that. There's the Rumaila power plant that takes gas from the field for power generation. I think it was built about 7 years ago, and they have these gas turbines at the power plant that have these small beta emitting sources as part of the ignition mechanism. But that's the only beta emitting source I'm aware of at RU. We then get to gamma, and gamma radiation is it's the one that's used most often. So it's the one that has utility. So gamma radiation is used for nucleonic gauges, so industrial gauges for looking at levels inside vessels. It's used for industrial radiography. It's used in lots of well logging tools. I'm sure those of you who've got quite a lot of experience will probably have come across gamma sources being used for a number of different things. The reason gamma radiation is so often used for measurement is it can penetrate through a lot of material, and therefore that property can be used to basically do level detection, non-destructive testing, all sorts of things. It's a really, really useful radiation. But you need very dense materials to stop it. So things like lead, sometimes we even use depleted uranium as a shield against gamma radiation. And the next thing I'm going to say depends on what physics background you have. Some people disagree with this, but from a radiation protection point of view, gamma and X-ray, we separate the two of those based on how the radiation is generated, how it is actually created. Now, this is the convenience thing, and scientifically it's not quite correct, but when we talk about gamma radiation, we are generally talking about a radioactive source emitting these high energy photons. When we talk about X-rays, we are generally talking about a piece of equipment that generates X-ray radiation by use of
انت
an
ممكن
an electrical generator, like you'd find in an airport at a baggage scanner. So that's the distinction we make. If you speak to a lot of physicists, they'll make
Yeah.
the argument that actually they're physically very different, and gamma radiation is higher frequency, higher energy than X-rays. But that that's an academic point, and we need to be practical here. So if we talk about gammas, we're talking about a radioactive source. If we talk about X-rays, we're talking about a radiation generator. Okay. Now, radiation generators are used at RU. They're used for industrial radiography, for NDT. They are used for security scanning. There's a medical set within the clinic at RU HQ. So X-rays are used. Gamma radiation is also used. There are lots of contractors working in the field that use gamma radiation for industrial radiography and for well logging operations.
Yes.
Where we also find gamma radiation is in much of the norm. Okay, now this does depend on which system the norm comes from. Okay, so there are differences in how norm's deposited depending on the fluids that are flowing. And we don't really come across much gamma in gas systems. Okay, so that's a really important point, and it's particularly important when we talk about the instrumentation that's used, how we choose the right probe checking for norm. Okay, so in gas production systems, there's very little gamma radiation in the norm. And so we have to look for alpha and beta. But in oil production and in produced water handling systems, which is actually the vast majority of the process across RU, there is gamma there. There's also alpha and beta, but there's gamma, and gamma is easier to detect than alpha and beta because it's not as easily stopped. So if you've got layers of oil, layers of water between the contamination in your probe, that will absorb all of the alpha radiation and it will absorb some of the beta radiation too, but the gammas will be able to get through that. So we give ourselves the best chance by looking for gamma if we expect it to be there. Okay, so I'll come back round to that later on. I am fully confident that given all your academic backgrounds that you are quite happy with using different prefixes. We always keep this in here just to make sure people are aware, but when we prefix a unit with micro, we mean 10 to the power minus 6, 1 millionth of the base unit. Milli, 10 to the minus 3. These two very often get used for prefixing units of radiation dose. As I'm sure you're aware, working in micro sieverts per hour for dose rate is much more convenient than working in sieverts per hour, because the sievert is a very, very large unit of radiation dose. And when we're talking about radioactivity, particularly with sealed sources, maybe less so with norm in the day-to-day, but we often use the larger prefixes. A typical radiography source, for example, will be in the region of several hundred gigabecquerels. So it's much more convenient to use these prefixes. So make sure you're comfortable with those. In particular, you need to be comfortable with micro and milli. Now, the prefix names in English, micro and milli, both start with M. And they are the most commonly mixed up when people are writing them down with the symbols. So milli, the larger of the two, is denoted with a lowercase m, micro with the Greek letter mu, which is like a U with a little tail on it. If you're ever unsure, and I don't want to insult your intelligence, but if you're ever unsure about which symbol to use when you're writing down a dose, if you can't remember, just write the word. Okay, so if you know that you're working in micro sieverts, but you can't remember if it's you're out in the field, you're filling in a form, you can't remember if it's the U with the tail or the lowercase m, just write the word micro. It's the get out of jail free card when you're on the spot. But I'm sure you guys are familiar enough with this that you won't get this the wrong way around. But really important when we're talking about dose, because there's a factor of 1,000 difference between microsievert and a millisievert. Okay, so it's crucial that we get that the right way around. The measurements that we use for radiation, some of them are useful for practical radiation protection, some less so. We have radioactivity, exposure, absorbed dose, and effective dose. Now, of the 4 of those, the only 2 we're really going to talk about are radioactivity and effective dose. Okay, exposure, very useful for some applications, but it's a much more sort of scientifically useful unit rather than a practically useful unit. Absorbed dose, again, we're working in terms of risk, and absorbed dose depends on a lot of things what the risk actually is. So absorbed dose will depend on the type of radiation, depends on which part of the body is exposed to work out the sort of detriment or risk to life. And so we're not necessarily that interested in absorbed dose either. Effective dose, however, takes those different factors into account. An effective dose is a way of quantifying the risk. So very, very useful unit in practical radiation protection.
Yes.
Where you would see absorbed dose being used would be in medical applications, for example. If you went to a hospital and they were going to give an X-ray, they would calculate the absorbed dose from that X-ray. It's very often worked out in absorbed dose. So, radioactivity, total activity, standard unit of the becquerel. Hopefully you're all very familiar with that unit. 1 becquerel means 1 radioactive decay per second. Almost all countries in the world use the becquerel. The big exception to that, can you guess which country decides not to use the becquerel?
Yes. We use curie in Iraq now.
Are you using that officially?
Yes.
Really? Okay. That's interesting. That's that feels like a US influence, because the IAEA is entirely in becquerels. Everything they do is in becquerels. Curie is quite a convenient unit when you're talking about like a large radioactive source. It's a 10 Curie source. Convenient, but we tend to encourage people to use becquerels because that's what the international standards are setting. So yeah, interested to get any information you have if the actual legislation in Iraq is starting to use Curies, because that's news to me.
Excuse me, what you say?
So if it is the legislation, the actual regulation in Iraq using Curies now?
Yes. We most time use the Curie, not becquerel, and regulatory body in Iraq. We familiar with the Curie more than the becquerel.
Really? Okay. That's interesting. So that means with the likes of Norm, I mean, we're talking about pico Curies, tiny amounts of numbers of Curies. Well, that's interesting. We'll probably need to have some further conversations on that to decide how things, if things need to change at RU with regards to the units they use. They have always used the becquerel at RU.
No problem. We can use the becquerel because we can also convert to the Curie. That's not a problem.
Yeah, you'll see that with Norm, the becquerel is actually a much easier unit to use. It's the opposite of your large sources. So with large sources, Curies make sense. The numbers work out really well. But with Norm, we're often talking about 1 becquerel per gram, and if you do that in Curies, it's very, very awkward units that you have to use. So it does tend to work out a lot better for Norm to use becquerels. So one becquerel is 1 radioactive decay per second. 1 Curie, of course, is 37 billion
37
radioactive
billion.
decades per second. So
Exactly.
big difference. Yeah.
That's great from the becquerel.
Yeah. So if you
Great
think
from the becquerel. More great from the becquerel.
yeah. Well,
Yeah.
one of the things that we often use for regulation is specific activity. Okay, so
Yes.
the IAEA has recommended levels at which something should be called radioactive, and it is often defined in terms of specific activity, which you can think of as like an activity concentration. The standard, the SI units for specific activity are becquerels per gram.
Milligram.
And as a general rule, IAEA for norm, 1 becquerel per gram. Anything above that is considered radioactive. So really, really quite low thresholds that we're working with. Now, related to activity is the property of radioactive half-life, which again, I'm sure you're familiar with. The notion of half-life is that all radioactive material over time will decay, it will become less radioactive.
Go to the stable stage.
Down to a stable state eventually. Now, some radioactive isotopes, they decay directly into a stable state. Norm is not so straightforward. Okay, you have
Yes. Yes.
you have essentially two different primordial radionuclides, which go through a very
Yes.
long decay chain before they reach something stable, and they have very long
Yes.
half-lives as well. But the half-life is a really useful measure of how quickly something decays, because if you were to look at, not that you can look at it, but if you were to isolate a single atom of a certain radioactive isotope, you could predict with a certain probability when it's going to decay, but you could never say with certainty. Okay, so it could, even if the half-life of that is 10 seconds, if you isolated an atom, it might not decay for 1,000,000 years. Okay, so we can only use probability for radioactive decay, and that's why half-life is such a useful measure, because it's not saying which atoms will undergo their decay, it's just saying how many of them will undergo their decay over a certain amount of time. So the half-life is the amount of time it takes for half of the radioactive atoms of the same type to undergo their decay and emit their radiation. And it's a fixed characteristic for each radioactive isotope. So just to give you a feel for how much it can vary, this top one, technetium 99M, that is one that's used in medical practices.
Yes.
6-hour half-life, so nice and short. It's beneficial from a patient dose perspective. It's a challenge from a logistics perspective. Okay, you can't make this at some central facility and then ship it to all the hospitals, because by the time it gets there, it's decayed. So hospitals that use this radionuclide, they tend to make it in the hospital. So they have these small desktop reactors that make this. Did you come across this, Heider, when you worked on the medical side?
Yes, we also use the technetium 99 metastable. Okay, this good for use for any patient for make the test. Okay, after I think after a half hour, make the imaging for the patient use.
Yep.
Okay, is that clear for you?
Yeah.
And
Yeah.
also used in thyroid gamma radiography or gamma scan. Okay.
Oh, okay. Yeah. 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 We've seen. Yeah. There's all sorts of things that are used in, less so now than maybe 10, 15, 20 years ago, but there's a lot of different radionuclides that have been used for nuclear medicine, where you actually inject it into patients. That thyroid treatment.
Yes.
So not thyroid imaging, but thyroid treatment, where you use radioactive iodine to actually control hyperthyroidism. That's not really done that much anymore. Certainly not in Europe, but I have seen it done on animals. So we still do it on animals, but not on humans. I don't know if it's still done in Iraq. I think they use a surgical procedure now instead of using radioactive iodine. But
Also using the iodine. Okay, but the difference on the situation of the patient. What we need the doctor from the patient.
yeah,
What the protocol? Which protocol you use this doctor to treat the patient or to any imaging or treatment?
yeah, yeah. So it's patient by patient, and it's all done on a risk profile as well. So you would take into the
Yes,
individual risks of someone.
radiation.
Could be based on age as well. Age is often a consideration. The older someone is, the less overall risk using radiation has
Yes.
on their mortality. So you wouldn't use radioiodine in a teenager. You just wouldn't do that, because the risks to them over the course of their remaining life expectancy will be higher than someone in their 70s, for example. So yeah, it's all patient to patient. The rest of the radionuclides here are all things that could be found in oil and gas. So cobalt 60 is occasionally used as a source for measurement. Not very often, because cobalt 60 is quite a difficult thing to control. Very powerful gamma emitter, very difficult to absorb the